Welcome back to Honors Calculus. In this video, we're going to be looking at the method of substitution, which is a tool we will be using to codify what we were talking about in the last video about how the chain rule can affect integrals. So without further ado, let me get my head out of the way and let's dive right in with the chain rule for differentiation. The derivative of a composition f composed with u of x differentiated with respect to x is the derivative f prime evaluated at u of x times u prime of x. So if I integrate both sides of this equation, on the left-hand side, the integral of a derivative is the original function, fundamental theorem of calculus. We get that f composed with u of x is equal to the integral of f prime of u of x times u prime of x dx. And the interesting thing we can do with this substitution is look at the right-hand side. We have a u of x here, and then we have u prime of x dx. Thinking about the way that differentials work, dx is a small movement in the x direction. U prime of x is the conversion between a small movement in the x direction and a small movement in the u direction, the rate of change of u with respect to x, change in u over change in x. So u prime of x times dx is something we can simply call du. And with that substitution, we completely ignore the x. We eat the x away from the right-hand side, giving us what looks like a much simpler problem that does not involve a composition of functions. To see what I mean, let's take a look at a problem that we've already solved. The integral of 1 over the square root of 5x plus 1 dx. We have already solved this problem. But I want to think about it in terms of this substitution method. Right? Our object function, f of x, is 1 over the square root of 5x plus 1. We can rewrite this thing as a composition of two functions. This is separately one over the square root of x evaluated at 5x plus 1. And so that's how we're going to perform our substitution. The traditional way of setting this up is we let u equal 5x plus 1. And then differentiating implicitly, we get the differential du is equal to 5 times dx. And then the differential of 1 is 0. Rearranging that second part, if du is 5 dx, then 1/5 du is equal to dx. And in our integrand, we're going to replace dx with what it means here, and we're going to replace 5x plus 1 with what it means here. And this substitution turns our integral into the integral of 1 over the square root of u times 1/5 times du. Cleaning that up a little bit, we have 1/5 times the integral of u to the negative 1/2 power du. Using the power rule, we know that the integral of u to the negative 1/2 with respect to u is 1 over 1/2 times u to the 1/2. And then the 1/5 out front stays a 1/5 out front. And as always, there's an arbitrary constant of integration. Cleaning up the coefficients, 1/5 times 1 over 1/2 is 2 over 5. Substituting back in, u is 5x plus 1, so u to the 1/2 is 5x plus 1 to the 1/2. And again, plus arbitrary constant of integration. For this particular problem, I believe that the method of U-substitution is longer and more tedious than thinking about it as a straightforward integral. But it works out the same. It gives you the exact same result, and it's essentially treading the same ground. So it's your choice which way you want to go. We can also look at U-substitution for a definite integral. If I have the integral from 1 to 3 of the cosine of pi x over 4 dx, I can look and see that this is a composition between cosine and pi x over 4. So I'm going to take the argument of the outside function, pi x over 4, and call that thing u. Differentiating implicitly, this means that du is pi over 4 times dx. For an indefinite integral, that's all we needed. For a definite integral, there is one more step I'd like to take, and that is the constant of integration. These constants are defined for values of x. We're changing variables from x to u. So we can change the limits of integration by evaluating u of 1 is pi times 1 over 4, or just pi over 4. U of 3 is pi times 3 over 4, or more commonly, 3 pi over 4. All that leaves here is to take my differentials equation and solve for dx to get that 4 over pi times du is dx, and then I can substitute everything in. My integral, instead of starting at 1, now starts at pi over 4. Instead of ending at 3, now ends at 3 pi over 4. And it's the cosine of, instead of pi x over 4, that's the thing we called u. And we found that dx is the same thing as 4 over pi times du. The 4 over pi can come in front of the integral. And we are simply integrating cosine u du. And we know that the integral of cosine is sine. Evaluating sine at the endpoints of the integration, we have 4 over pi times sine of 3 pi over 4 minus sine of pi over 4 sine of 3 pi over 4 is the square root of 2 over 2. Sine of pi over 4 is also square root of 2 over 2. Subtracting those off, we get 0 is the solution to this particular integration. Kind of an interesting result, but a useful one nonetheless. The real power of the method of substitution is that it allows us to take care of integrals that involve much more complicated looking expressions. I'm going to go back to an indefinite integral because it's going to save us a little bit of work. But let's take a look at something quite striking. The integral of 2x plus 5 over the square root of x squared plus 5x plus 7 dx. Solving this problem is more of an art than a science, but it's well within reach. The most complicated thing in this expression is that square root. If I can do something with that square root, I'm going to be very happy. So that's where I'm going to focus my energy. I'm going to let u be the stuff under the square root, x squared plus 5x plus 7. And if I differentiate implicitly here, du is 2x dx plus 5 dx, and the derivative of 7 is 0. Previously, I have solved for dx at this point, but I'm going to simply notice that if I factor out a dx, du is 2x plus 5 times dx. And by complete coincidence, otherwise known as this problem was very carefully designed so that this would work out, 2x plus 5 is exactly what's being multiplied by dx in the numerator of this fraction. So we can substitute in and find that this is simply the integral of du over the square root of u. All right, we'll rewrite that as u to the negative 1/2 du and use the power rule. M is 1/2. I'm sorry, m is negative 1/2, so m plus 1 is positive 1/2. We have 1 over 1/2 times u to the positive 1/2, which we can write as 2 times the square root of u, always plus some arbitrary constant of integration, and substituting back in, u is x squared plus 5x plus 7. So we can evaluate much more complicated integrals using U-substitution than we could before. Here's one that we've tried before again. Sine x over cosine squared x. We previously approached this problem by means of a trigonometric substitution. We used the properties of trigonometry to rewrite this in terms that we were able to handle. I would like you to think about this problem and see if you can instead solve it using a U-substitution. So very specifically, not just evaluate this integral in general, but pick something to set as u. Look where the most complicated thing is in the problem and see if there's something you can work with there. Pick a value for u, figure out what du is going to be, use that substitution to work out the integral, and then double check to see if you get the same thing that you got when you went through this problem in a previous video. Take a few minutes, see what you can do with that, and I'll see you in the next video.